Hello, thanks for joining us. I'm Pete Zielinski, Editor-in-Chief of Additive Manufacturing Media. Welcome to today's webinar titled Hybrid AM at Lower Cost, Metal 3D Printing on a Haas Machining Center, brought to you by SolidCAM. The platform combining metal 3D printing with machining is getting more accessible. In this webinar, SolidCAM and Phillips Additive Hybrid, powered by Haas, will talk about their collaboration and the technology and programming of a hybrid machining center. Our speakers are Brian Christoponis, General Manager of Phillips Corporation's Hybrid Division, and Peter Genovese, 3D Printing Engineer with SolidCAM Additive. As they speak, please ask questions. You can do that using the Q&A section at the right of your screen. We will see the questions entered in that box, and at the end of the talk, we'll answer as many as we can. So Pete, I think we'll start with you. If you're ready, please take it.
Great, thank you very much, Pete. So to start off, we'll just give a little bit of background into kind of who SolidCAM is and what we're looking to do here. So SolidCAM has been a global leader in the CAM space for almost 40 years now. And over those last 4 decades, we've always tried to keep our finger on the pulse of the industry to try and stay one step ahead of where technology is going in this ever-changing world of manufacturing. And it's that action of trying to stay one step ahead and making sure that our software is always relevant to the new technologies that are coming out that has really pushed us forward over these last 40 years. So whether it's our simultaneous 5-axis, our control of some of the most advanced mill turn and Swiss type machines on the market today, our patented eye machining and technology wizards, all of these are direct results of us trying to keep track of where technology is headed and try to make sure that our software is always relevant to those ever-changing technologies. So as we saw that, Swiss machines were becoming more and more the cornerstone of modern manufacturing, they became increasingly complex and more and more capable with every new iteration. We made sure that our software is able to just natively handle any type of crazy machine that those engineers would come up with. So we have unlimited channel synchronization. So when a company like Tornos comes out with a machine that's got 40 axes and half a dozen spindles, we can support that natively because we knew that was the direction that technology was going in, and we wanted to make sure that our customers had access to the most capable platform that was available at the time. And a similar trend that we've been keeping track of over the last few decades has been additive manufacturing. When 3D printing first came out of the market, it was this really new, really niche type of technology. And while it was really cool and really enticing for a lot of people, it was still a little unrefined, a little not quite polished yet. Technology was awesome, and there were a lot of thoughts and theories about where additive manufacturing would fit in and how much it's going to upend traditional manufacturing. But over the last few years, we started to see more and more of those promises actually be delivered on. The technology has stabilized and it's become much more widely adopted in the market. And really what we've seen is that additive manufacturing is here to stay. This isn't some fly-by-night fad in the industry. It's become an integral cornerstone of so many different industries. When you look at, say, medical devices, for example, 3D printing is at the heart of so many of those medical implants these days that it's pretty much a technology we can't be without. So while we don't think that additive is ever going to completely replace or supplant those traditional methods, we do think it's going to continue to augment and enhance our traditional manufacturing technologies like CNC machining. And so to keep with our theme of keeping up with the changing times and trying to stay relevant as we get more and more technologies coming to market, we launched Solocam Additive in 2022. And the entire purpose of this new branch was to become experts in the combination of 3D printing and CNC machining. And we do this in a couple of different ways. So one of the first things that we do is our 3D printing and hybrid manufacturing consulting for machine shops. So this is where we go into a shop and we look at their existing pool of resources, technology, the personnel and staff and expertise they've already developed, and we see what types of parts are they working on, what types of customers they have coming in the door, and where additive technologies could fit into those existing workflows and best to enhance their existing technologies. Because again, additive is not going to come in and replace or completely upend the way that they're doing things today, but it really works hand in hand quite well with the existing technologies, whether it's to gain additional capacity or to produce more complex parts. We try and find those little niches where additive can slip right into that workflow. Another way that we help doing this is that we are a value-added reseller for desktop metal products. So some of their products we think are very uniquely suited for these types of machine shop environments, specifically binder jetting technologies in general, have opened up a really interesting world of very cost-effective kind of medium-scale production. For the first time in years, you saw an additive technology that was capable of producing hundreds, thousands, even tens of thousands of parts in a single system. So this really fit in quite nicely with our existing portfolio of machine shops and how we thought additive could really help to benefit them in the long run. And the last thing that we do, and kind of the main topic of today, is our hybrid CAM solutions. So obviously, CAM, computer-aided machining, is in our blood. It's what we do. It's who we are. And seeing that there are more and more of these hybrid machines, these machines that combine additive 3D printing technologies and subtractive technologies all within one machining center, seeing them become more and more common and more popular, we knew that there was a need for this in the market. So our mission statement: we believe that to stay competitive, the shop of tomorrow will need to embrace hybrid manufacturing. We're here to help guide our customers towards that future by putting this technology in their hands and helping them be successful with it. So before we talk about the CAM for hybrid machines, let's talk a little bit more about what hybrid is and what it actually looks like. So just to kind of, keep things sane for us, we break into kind of two broad categories. All hybrid is combining additive technologies and subtractive technologies. And generally we refer to these as either sequential or simultaneous hybrid technologies. So sequential technologies are where you're going to take any type of additive technology that you might be interested in, whether that's FDM, DMLS, DED, and you'll print your part from start to finish. Then you'll take that part, move it into an entirely different machining center, and you'll machine that part in traditional methods. Has a tons of benefits to it, as well as a couple of drawbacks that we'll talk about in a minute. Contrary to this, we also have simultaneous hybrid, and this is a little bit newer on the scene with companies like Melto and Phillips coming onto the scene to provide these technologies to the greater audience. So this is where we have a single machining center that is capable of both additive technologies, 3D printing metal in a lot of cases, and then subtractive machining, all within that same setup, within that same machine envelope. So let's talk a little bit deeper about sequential hybrid manufacturing, some of the pros and cons there. Like I mentioned, you can pick and choose pretty much any additive technology that you're interested in. And that's one of the main benefits of this particular type of hybrid manufacturing. Because you're not constrained by, being able to actually combine physically these two separate technologies into one ecosystem, you have pretty limitless possibilities for the combinations there, right? So you can print with whatever technology you want, and you can post-process with whatever technology you want. And while it's very powerful, it also does have a couple of key drawbacks. One of the main ones here is that obviously you now have multiple setups, multiple operations, and multiple machines you have to transfer your parts between. And those in the machinist trade know that those are all opportunities to introduce more errors into that process. And while machinists have gotten very good at transferring parts and redoing setups and creating fixturing and jigs, every opportunity we have to eliminate those sources of error is always beneficial. Another potential drawback that you have with this type of technology is that you're a little limited in what your options are for those post-processing steps. So because this is reliant on 3D printing a part completely from start to finish, and then transferring over to a different machine to do the subtractive operations, you're limited into what you can physically access with those traditional subtractive tools. So in the example we have on screen here, this is a little conformal cooling block for maybe an injection molding die. And we're obviously able to surface the exterior of the part no problem on a subtractive machine. It was actually done on the Hermley right behind me. But what we can't access are those internal channels. Those have to be left in the as printed state because there's really no other way to get at them. In a lot of cases, this might be totally fine, but this is a notable drawback of having to do things in this sequential step-by-step method. Simultaneous hybrid manufacturing, on the other hand, is kind of the exact opposite. Instead of having these two completely disparate processes, we actually take them and put them in a single machining center that's capable to do both the 3D printing and the traditional subtractive operation. The Phillips Hybrid is a perfect example of this. So obviously, one of the big benefits here is that you kind of get two for the price of one. When we're talking about modern machine shops, the square footage in that facility is an incredibly valuable asset, one of the most valuable assets that they have. And so for a shop to have to decide between, do we buy a new additive tool, do we buy a new subtractive tool, that can be a difficult decision. But here you actually kind of get the best of both worlds. By having this one machine on the facility floor, you can now choose day by day, week by week, what technology is more useful or more relevant to your current capacity and current needs and current workflow. Obviously, you can combine them both, but it also means you have access to both separate technologies in the same footprint. Another big benefit to having both technologies in this single machine with this single setup is that now all of a sudden you have access to regions of the parts that you wouldn't otherwise be able to access. So a great example is that little cross tubing pattern that you see in the bottom corner there. Let's pretend that the inside surface finish of those walls is really critical to us. Well, if we did this as a kind of stepwise process where we print the whole part and then machine it, we're going to be a little limited in being able to access the interior of that part. But by having it all done in the same machine, we can choose to print, say, 10 or 15 layers, switch to our subtractive tooling, machine the outside and the inside of the part, and then continue on our way. So all of a sudden, we have much more freedom of design, and we can have much more complex parts that still allow us the full level of fit and finish that you can get with the traditional subtractive operations. So these hybrid platforms introduce a ton of new advantages into the market, but with that comes a lot of complexity. These are very complicated machines, and something that we've seen in this industry is actually something we've seen before on the consumer end, is the machine tool builders, the system integrators, the OEMs, they've produced really quite incredible pieces of hardware that are capable of so much more than they're being used for today. And a lot of times what tends to happen is that they're actually held back a little bit by the software that's available and on the market. We saw the exact same thing happen with consumer 3D printing just in the last couple of years. We took these machines that had been, we'll call it a decade old at this point, very traditional mechanical systems, and just with some software tweaks, input shaping, clipper, pressure advance, just the ways that we control these machines, we were able to gain 2-3 times the print speed without changing anything mechanically about these systems, purely with a software change. That's kind of the same state that we're seeing the industry at currently with these hybrid platforms. They're incredibly capable mechanical systems. Now we just need the software tools to unlock the full potential of those platforms. We've talked with a number of users in the research and development fields that are utilizing these technologies, and the ideas that they've come up with for what they should be able to use these machines for are absolutely mind-boggling. I'm incredibly excited to see what they'll be able to do once they have the right tools in their arsenal to really unlock those capabilities. Now, like I mentioned, this technology is advanced and complicated. So this isn't the kind of thing we can develop in a vacuum. Obviously, we have the extensive knowledge on the CAM side, but we're new to this 3D printing just like everyone else. And so that's where partners like Phillips come in that really make or break this entire project. They have extensive knowledge on the subtractive side, but now they also have that knowledge on the additive side. And more importantly, they understand the union and hybridization of those two technologies. They're working directly with the customers, with the beta testers, with the people that are really pushing the cutting edge of this technology. So they know the customers, the needs, and the technology. And because of that, we're able to really leverage their expertise in this field and develop a CAM software and tools that we know are going to be useful and crucial to people in this industry. Now, we talked a lot about the CAM side, so I do want to show a little teaser here. We are actively developing our hybrid CAM toolpaths for systems like the Meltio platform. Now, keep in mind, this is still an active development, so I had to kind of twist our developer's arm a little bit to get a bit of a teaser for you guys. So he wanted me to add our typical disclaimers, right? When it comes to software, we want function first, and we worry about form later in the process. So it may not be final, but you should be able to see a lot of the core functionality here today. For anyone who's used SolidCAM in the past, a lot of this should look very similar. It's all more or less the same UI, UX that we have previously. Here, we're doing just some relatively simple operations. We're adding this little hexagonal part onto a flat platen. We're just choosing our tools, defining our containment boundaries, and specifying what types of patterns we'd like to use to actually generate this 3D model, this 3D part. And like I mentioned, we can do this in a couple of different ways. So we can do single layers at a time, and then we can go back and machine those layers so that we have better tool access. Or we can fill the entire volume and just print the whole thing in one shot. It really just depends on what we need. And of course, because it's all done natively in SolidCAM, we have full machine simulation as well for things like collision avoidance and crash detection. So you can see we had our Haas head come down and machine the part to kind of prep the surface. And then the Meltio head comes down to actually deposit our material. So I hope you guys enjoyed that little bit of a peek behind the scenes as far as the CAM development side, with hopefully some more good things to come in the future. And with that, I'm going to hand it over to Brian to tell you a little bit more about the hardware and just what that platform is really capable of.
Thanks, Pete. So first, I want to introduce Phillips Corporation for those who may not be familiar with us. We've been in business for over 60 years with a large federal sector and commercial sector. We've been involved with Haas automation for over 30 years and have over 30,000 machines installed. We have a variety of different divisions. On the East Coast, we have our commercial group, which usually typical geography is South New Jersey to Northern Florida. We also have our federal division, which covers the entire world for U.S. Department of Defense, as well as a large Philips India team. And we also have a co-op in China with Philips Taitung. And overall, our mission is to create legendary value for the manufacturing community by unlocking solutions to propel capabilities, profitability, and productivity. And really through this mission is how we came up with our hybrid solution. And Pete, if I go to the next slide for me, please. So we have in this image one of the first UMC750 Haas machines that we actually integrated with Meltio's technology. And we'll get into Meltio's technology in a few slides. But overall, this is a directed energy deposition additive technology that we have coupled with Haas machines. So Pete, if you can move to the next slide. We have two videos of our system running. One is on this UMC750, the video on the left, where we're doing some simultaneous deposition. So we're depositing with all 5 axes of motion in this UMC. And then the video on the right is another hybrid machine where it is a VF with a TRT. So still 5-axis machine, just a AC configuration versus a BC configuration. Go to next slide. The reason we selected Meltio is all about their type of deposition. So with Meltio, they have a laser-based wire-fed technology. And what we feel when it comes to hybrid solutions, wire is really key. We're using a feedstock that is 100% consumed. We're not wasting any material like we've seen with some of these powder blown systems. And we have a lot of control with a laser power source. So really being able to do intricate features with the laser wire technology. So this is kind of a segmented view of the Meltio head and Meltio's patented technology. So it's a coaxial wire-fed solution surrounded by multiple lasers. And the multiple laser configuration does a couple of things. Overall, it keeps, laser power source costs down because we're using 6 independent 200-watt lasers rather than, a single 1 kilowatt power source. The big benefit, though, for a multiple laser wire-fed system is the fact that the wire is in the center of the melt pool and surrounded by lasers. And what this allows us to do is feed in any direction. So we can feed in any XYZ combination as well as multi-axis deposition, where some technologies out there with side-fed wire allow you or force you to feed in one direction, where you need to have essentially the feedstock behind the melt pool, where because we're center fed, that issue goes away. It makes programming of this technology very straightforward, very similar to any other CNC toolpath in terms of kind of process flow, just using particular additive toolpaths. Very easy to service with a redundancy of 6 lasers as well. And overall with this process, we have a lot of benefits. So a lot of questions that I get is kind of what's the resolution or how much overbuild you need to have to allow for machining. And it is somewhat feature dependent as well as part size dependent, but general rule, about 1 millimeter or 40 thousandths per side is how much I will overbuild and then machine to final net shape. Now, as you get into larger features, parts that are, multiple feet in length, you may need to add more material, or if you have a more complicated 3D surface, you may need to add, up to 1.5 millimeters or 60 thousandths of an inch, but certainly not an excessive amount of material. Really reduces the amount of roughing time you may have with a conventional process compared to a hybrid one. Overall layer height, nominal is about 1 millimeter or 40 thousandths high. And we have extremely great density with the Meltio technology. So at 99.998% density, really gives you great mechanical properties and overall, exceeding kind of cast properties when you compare to, conventional castings. So move on to the next slide. With this type of technology, we kind of have the middle of the road in terms of application. So powder bed fusion certainly has their market, for very small, intricate features. And then when we talk about, large format metal printing, with a WAM technology, we're kind of in that middle of the road. We can print large parts. We also have very good resolution with the Meltio technology. So we're in that, ballpark range of cubic volume, say 24 inch by 24 inch by 24 inch cube. Parts that fit inside of that usually are good Meltio or Phillips hybrid candidates for the technology. Overall, Meltio has done a lot of work in the last couple of years to develop parameter sets for the materials listed. It is an open source platform, so you can use any welding wire that you can source, but Meltio does offer their own welding wire with the materials listed here and the parameters that go along with it. And the mechanical properties that they have tested are available on their website for all the materials listed in this sheet. And then on the next slide, we'll talk about, the differences between wire and powder. But before I get ahead of myself, I wanted to talk about the additional amount of materials that we've done at Phillips Corporation. So while Meltio offers, roughly about 10 different materials that they have parameter sets for, we've done probably another 15 to 20 materials that are all slight variances. When we talk about stainless steel, if you can find a stainless material in wire form, 17.4 is a listed material from Melto. We've also done it Phillips 15.5, different variations. So while you may only see 8 to 10 materials listed from Melto, the platform is completely open, and we've done a significant amount of similar materials to that portfolio. And we really believe that wire is the solution for our directed energy deposition hybrids. Mostly, in terms of protecting the machine tool, we don't have to worry about any type of hazards, with reactive materials like aluminum, titanium being in a powder form. With wire, it's inert, so we don't have to worry about, any, PPE to handle the wire. It's not a concern compared to powder. As well as storage. We don't have to worry about storing our wire in a special enclosure, simply keeping in a low humidity environment to prevent from oxidation with most materials. You also don't have, the coolant contamination like you would have with a powder system inside of a machine tool. Wire is much easier to handle, as well as changing over. So a simple wire change could take a matter of minutes, depending on the system. No more than 10 with any of our systems, depending on how long the run is from the wire feeder to the actual deposition head, compared to a powder system where you're having to do very thorough cleaning of all your lines to make sure you don't get cross-contamination. Not really something we have to worry about when it comes to wire. And overall facility requirements, really the same concept is, having to wear PPE. We don't have to worry about any type of hazards with wire. And we'll go to the next slide, Pete. Overall cost as well between wire and powder. In some cases, it can be 10 to 1. But the big takeaway is that we're using all of this feedstock, where with most blown powder directed energy deposition systems, you're really using anywhere from best case scenario around 70% feedstock all the way down to as low as 40. So even though in some cases we could be 10 to 1, the cost is actually even more significant than that. Could be 20 to 1 because we're actually using all of this feedstock versus a 50% utilization rate. And then, as Pete mentioned, kind of the overall hybrid manufacturing process is really having a CAM software that supports both additive and subtractive operations. So we're programming both sets of toolpath inside of one software, creating the actual G code to run on the machine, and then printing, depositing, and then doing the final machining. And depending on the actual application, really depends on what the part requirements are for. We find ourselves completing parts from scratch where we would print the entire part and then doing all the post-process machining. But if we have a reason to go back and forth, that's certainly something our system can handle, really to get access or reduce the stick out of a tool, to have a nice rigid setup where we can go back and forth and print machine to reduce those kind of extended tools that might be required. Different slicing strategies. So a general kind of planar slicing, very similar to kind of normal FDM printing, is what a planar slice would be. Non-planar slicing is certainly a fun one for our 5-axis machines, where we can start tilting based on a guide curve to slice in multiple axes. So this type of funnel is a great example of that. Radial slicing, if you're doing spline or a sprocket type geometry around a shaft, where you're rotating about a certain axis as you're slicing. And then one of my favorite ones is doing a spine slice where you're giving a drive geometry where we're actually changing feed rates to generate a non-linear layer height. So this will allow you to do tubular types of shapes where we're automating the change in feed rate to achieve that curvature. And some of the applications that we find ourselves kind of working on the hybrid side with these directed energy types of systems, feature addition, where we're taking a substrate, in this case, we have a shaft, we're depositing some material on that. So the bulk of the actual component might not be the deposited material. So what this allows us to do is reduce the amount of cycle time for printing if we can avoid printing a generic shape. So if you can find a particular diameter stock that has one little feature in terms of your part that you can just print a single boss on, you're going to save a lot of time versus trying to print that entire shaft by doing a feature addition. Repair work for a hybrid machine is kind of certainly our sweet spot. So the biggest thing is that you could establish a surface on a damaged component by machining away that area. So you might have a broken corner or cutting edge on a particular part, machine away that surface, and essentially create your datum surface by using that first machining operation to clear away and essentially normalize the surface that you're about to deposit on, then start printing, and then do your final machining all in one setup. So repair work is one of the big sectors that we focus on. Cladding, very similar to feature addition. It's really one person's kind of perspective is how much material you're actually depositing. However, where I draw the line with cladding is it's much more simple geometry. I'm taking a substrate in case of a shaft and depositing a single layer or, one or two layers. I'm not really printing a unique geometry like I would with feature addition, but feature addition and cladding certainly very close in terms of applications. Casting replacement, we do quite a bit of steel and stainless steel casting replacements, where if you have a very low quantity run for a custom casting, can certainly be advantageous to use this type of technology to print your near net shape and do all your machining work. And then one of the big advantages of Meltio is the fact that we can do multiple materials. So we have the ability to switch between two different wires on the fly, not at the same time, but basically you can start out with another material and then switch. It takes about 5 seconds to switch between materials. So even on a given layer, you can have two different materials and go back and forth. So the multi-material example in this case, some of the peripheral edges are in a harder alloy. One of the caveats, the materials must be compatible for welding. So, a lot of stainless and Inconel blends, as well as, ferrous steel materials and stainless blends as well. But really, good benefit for hard facing as well. So adding a much higher hardness material where you need it, and using a much cheaper alloy to do the large majority of the print. Some examples of 3-axis cladding and 5-axis cladding, putting a stainless layer on a steel substrate just in 3-axis using a planar slice, and then doing some cladding on a shaft. Both, kind of general purpose cladding examples here. Casting replacement, this was that part that we actually worked on at IMTS back in 2020, made about 15 of these components during the show, where this reduced the lead time to get this custom casting made for a customer. And we were able to really only machine the areas that we needed to. So this is essentially a funnel where we needed to machine the OD and ID of both ends, where it goes from a round flange to a rectangular flange. So didn't have to machine the outside or inside of the curved portion of this piece, but certainly could if the requirement was there. And then I've seen some of the questions popping up in the chat. So this is probably one of the kind of area that we get the most questions of Phillips is, how is the system programmed? Right now, we use a series of M codes to communicate between the Haas controller and the Meltio controller, turning on things like basically laser security and making sure that we do have a layer of protection. That way there's no way to open the door while the laser is on to protect the operator. We turn on things like the actual lasers, deployment of the head. So the head is only deployed when we're actually printing, retracted when we're doing conventional machining. And we also have an additional M code that will allow us to apply a head shift in the background. So that way we handle that XY shift between the milling spindle and the additive head. Overall G-code format, very similar to any other normal Haas machine without an additive head. It's few additional M codes, and just kind of this overall sequence where we're activating our additive commands, turning on our lasers on and off as we deposit material. And one of the, really new developments that we've made is we're actually passing variables from the Haas machine now to the Meltio system. So we're able to control laser power, shielding gas, wire feed rate, all from within the Haas controller now. So that's something we'll be rolling out probably in the start of 2024. But we're constantly making developments to make the hardware and software side of things on the CNC control much more user-friendly. And we think we've done a really good job in the last 3 years working with Meltio. And the systems operate extremely similar to a normal CNC machine. A few days of training from a person who's familiar with the Haas platform or machining in general, and you're up and running and printing parts. Overall steps when we talk about the integration is we need to mount the actual deposition, Meltio deposition head to the Haas machine. So we make our own adapter plates at Phillips, and this allows us to align the Meltio axes square to the Haas machine. So we have adjustment built into our designs, and we mount essentially these adapter plates behind the factory Z-axis spindle cover, the way it looks, and feels like an OEM installation where everything is very seamless. We install laser safe glass on all the Haas windows to prevent the operator from the laser wavelength. And then also put additional safety interlocks, for example, on side doors. That way there's no way for an operator to open a side window like you potentially could on a conventional CNC machine because of the laser safety aspect. And then, we install the actual conduits, which in the fifth picture on the right shows the conduits going into the top of the deposition system. We do all of our integration on site, whether it's a retrofit or a brand new machine that we sell. It takes us about 1 to 2 weeks, depending on Haas model options from the Meltio side. But within that 2-week range, all done on site. And then across the different Haas machines, we integrate pretty much on all Haas VF machines, the large majority of UMC machines, and the VMs and tool room products. Some of the machines, we can do like the smaller TM0s and VF1s, but you get so much more of a build volume when you use these larger format machines on the left that for the cost of integration, it really makes more sense to start out with a larger machine travel on the Haas side. And then there's some machines that it physically can't, be integrated with, some of those smaller drill tap machines or drill mill machines just physically can't actually have the Meltio system fit inside the travel.
All right, so I think that about does it for that. And of course, we can't have an additive manufacturing media webinar without mentioning we have Form Next Forum Austin coming up very, very soon. You'll be able to find both us at SolidCAM and Brian with Phillips over at the booths 231 and 331 respectively. So we hope to see a lot of you there.
So gentlemen, we've had a few questions come in, so let's get right to that. One audience member commented, we've seen wire-fed laser deposition tried in our industry, which is aerospace. The issue seemed to be that the stress in the part caused severe distortion during machining. How have you overcome this?
Certain materials are really going to be highlighted. There's going to be more stress when you weld Inconel like 718 versus a 316L stainless. But a lot of things can be done to reduce that. We're using cooled build plates to minimize how much heat we're having in that overall build. So that's definitely been one way, is using cooled build plates to reduce basically how much heat you're putting into a part to reduce stress. But there are certainly going to be applications that you're going to have to do a in-between heat treatment to reduce stress. Most of the materials that we've printed with stainless, ferrous, steel materials, we haven't seen a lot of distortion. And that 1 to 1.5 millimeter overbuild has been significant, where we haven't had to exceed that and haven't seen warpage exceeding that.
Another question asks about the capability of infill patterns. Is that a possibility? What types of infill patterns are available?
Yeah, Brent, if you wanted to start off for what you guys are doing today, and I can throw some comments as well.
Sure. So infill, as a general rule, for our technology, you're trying to keep overall bead length as short as possible. So we find zigzag infill giving us really great density. We have a bunch of different options. We've done most of our work with solid parts using a zigzag style infill, but doing a profile style infill that follows the outer or inner geometry of a part is something that we certainly also have done pretty thoroughly. And then you start having combinations of that. So you might be doing 2 or 3 or even 4 profile passes, and then with a zigzag style infill. We can also do one-way infill, but one-way infill really is a lot slower because we're having to turn on and off the lasers every single time we do a single pass. And with the multi-laser technology, we haven't seen any benefit from a unidirectional infill. So zigzag infill and profile style infill is probably the big two for us.
Yeah, and from the CAM side of things, generally we have more freedom on the programming side than we do on the actual physical requirements of the system. So like Brian mentioned, this is at the end of the day a welding process, and there are some practical limitations to what types of toolpaths you may want to implement in that solution. So on the programming side, we can add a bunch of different toolpaths in there, but you're going to be more limited by whatever actual technology you're using on the hardware side of things.
Another audience member asks, is it easy to replace the extruder from single to multi-material?
So with the Meltio technology, it's already included. So when we have a single versus dual wire system, it's an external feeder on the hybrid side that dictates dual wire. So for our technology, we're not changing out any head components. The hardware is already there. It's simply an option with an external feeder that allows you to have dual wire.
What are the Z direction properties of the part like? Assuming a straight vertical buildup, what's the component like in the Z direction?
Yeah, I think that's one of the really unique aspects of Meltio's deposition technology. In terms of tensile strength, extremely close, Z-pool versus XY. So mechanical properties, I would say 95% of what you would get with XY direction compared to Z direction.
Have you done any application studies, projects with recycled materials?
I personally, at Phillips, we have not done any recycled materials currently. I think, there's certainly applications that would make sense. When we talk about machines that are remote locations, certainly open to testing, but we have not done any recycled materials to date.
As you mentioned, you get a lot of questions about the control and programming, and some of that you've addressed as you've gone, both of you. But here's one that kind of swerves into that, and the audience member asks, can the 3D printing head be programmed at the controller?
Technically, yes. I think, with my background in machining, the idea comes up about programming CNC machines at the controller. When we start getting into 5-axis and simulating a machine, it's in the same realm. Yes, you technically can create toolpath at the control. It's at the end of the day, it's just G code. But with CAM software solutions and the technology that we have and the computing power that we have, control programming to me is kind of a thing of the past. Everything should be done on an offline system.
Yeah, as a CAM company, I feel obligated to say that's what it's there for. I know some very competent machinists that can, work their magic right on the controller, but obviously it's there to make everyone's job easier. So if you had to, you could, but you generally don't want to.
So this question refers to the sample part you showed that was a casting replacement, and the question asks, getting a smooth surface Getting a smooth surface in XY seems intuitive, but how do you machine a smooth interior surface in Z using your example of a bent tube?
Yeah, that's where you would certainly have to segment the toolpath. If we needed to machine the inside or outside of that curved geometry, you're going to have to, especially for the inside, it's a physical limitation where you're not going to be able to get a lollipop style ball mill inside at a certain curvature. So that's where you'd have to print, maybe 15 degrees of that bend radius, and then machine the inside of it, start printing again. And one of the things, and it actually ties back into distortion, what you don't want to do is, let's say, print from 0 to 15 degrees and then machine from 0 to 15 degrees and then start printing again from 15 to 30. You need to leave kind of a thermal barrier. That way you're not distorting what you've previously established. So what you would want to do is print between 0 and 15 degrees and then machine from 0 to 10. Then print from 15 to 30, and then you might start machining from 10 to 20. That way you're leaving a standoff distance to provide a thermal barrier and not distort what you've previously machined and not create an overhang condition. So if you're machining up to where you start depositing again, you're going to have some type of overhang condition. And yes, with multi-axis, we can tilt the head to alleviate some of that concern, but you're still going to be fighting that thermal distortion.
You mentioned the range of materials, but could you touch on that again? And specifically, this audience member is asking about, is aluminum a possibility?
So right now, aluminum is one of the materials. Aluminum and copper are really under development with Meltio. Outside of aluminum and copper, if you can find it in a wire form, there's a good chance that we can process it with our technology. So nickel-based super alloys, certainly a sweet spot for this type of technology because of how difficult it is to machine, as well as high cost for billets or castings of, Inconel 718, 625, different Monel materials, Hastelloy materials. That's certainly a great application, or can be great applications for us. But a wide variety of stainless materials, titanium as well, titanium 6.4, is very common for us, as well as a pretty broad spectrum of steel, from tool steels like H11 and H13 to higher tensile strengths, like a ER100 or ER120 welding wire. And I think one thing that I may have missed on is that we're using commercially available MIG wire. So this is not some proprietary welding wire specific for laser technology. We have worked with different wire manufacturers for kind of niche applications, but the large majority, in the 99% plus range, this is all commercially available welding wire.
What protection or shielding does the Meltio head have from machining coolant and chips, and how much of the work envelope does the integration take up?
So a couple of different questions on that. We use argon for shielding gas. That's kind of the overall arching process gas that we use. We are experimenting with nitrogen. The gas also protects the optics. So while we're printing, the gas is flowing around the laser optics. In terms of machining, when we're doing machining work with flood coolant or through spindle coolant, obviously there's going to be quite a bit of coolant mist in the machine. The Meltio head retracts up into a deployment mechanism, which has trap doors that protect the Meltio head from coolant and chips while we're machining. We also lock out the coolant pump while we're doing additive work. That way there's no way to accidentally have an end user turn the coolant system on while you're printing. My kind of joke is that it would be an expensive accident if you were turning the coolant on while you're laser welding, but that's prevented with some macros that we have in the background. In terms of overall protection, we have systems, that we've built 3 years ago now, running flood coolant, every day, not having an issue with, coolant contamination on electronics or optics.
Is inert gas part of the Meltio head?
The inert gas, it flows through the actual optics, as well as it creates the inert kind of bubble around the actual process. So in the actual Meltio head, the gas is coming out of the gas nozzle, which creates that localized inert environment while we're welding. So we do not flood the entire chamber of the Haas machine.
Another viewer asks, could this technology be adapted to a CNC lathe?
So right now, when that's came up, because we're using lasers that are fiber coupled to our collimators, essentially our optics, one of the big issues or challenges that you have with the lathe is most lathes are turrets. So how do you mount the actual deposition head that's coupled with fibers to a laser source? And if it's mounted on a turret, that's not really physically possible. What you would have to do is have a robotic arm with the deposition head mounted to. That way you would have the door automatically open, have a laser safe cell around the lathe, and that's how we would handle it if you needed to have a process that was going to be put on a turning center.
This one's a good geometry question. On the spline-based slicing of the tubes, and you showed one of the tubes, it's kind of like wound back and forth. On that spline-based slicing, how are you managing the different bead heights between the inner radius and outer radius?
So one of the unique things about this toolpath is we're giving it a centerline spine curve, and based on the relationship between the spine curve and the actual geometry, meaning the internal radius versus external radius, we give the toolpath a slope function. This allows us to give it a nominal wire feed rate and linear feed rate, as well as a minimum maximum. And by doing this and tuning this kind of minimum and maximum of knowing what the process can handle, there is a physical limit of we're not going to be able to be, printing a 4 millimeter, 5 millimeter tall layer height. So there is a finite layer height that you can't violate. So normally our nominal layer height for single wall is around a 0.5 millimeter. For solids, it's about 1 millimeter. We can go down a little bit lower than that. So like when we're doing a spine slice, we can handle about 1/4 of a millimeter, about 0.010 of an inch, up to about 1.5 millimeter. So we give it essentially those 2 points on the curve that intersect with our nominal feed rates, and the software will compute the feed rates for us. So you're constantly changing feed rates, but maintaining wire feed rate. So wire feed rate in this particular toolpath is consistent, and we're able to alter linear feed rate.
Does SolidCAM support geometry like in traditional FDM 3D printing?
So from a software standpoint, the quick answer is yes. And I'm not sure if I mentioned this, but the kind of 2 target technologies that we're going to have for kind of the initial release will be DED platforms like this, as well as FDM, most likely larger format FDM hybrid machines. So yes, we will be able to support structures, but that will be more technology dependent. So there are, again, some practical limitations to when you may want to use certain types of supports or certain support styles. But yes, the software will be able to handle that as well.
This next question sort of refers to the cooled work surface that was mentioned before. This audience member is asking, can heat be dissipated through work holding for small parts without a build plate?
Absolutely. So we're using essentially a subplate that we run water glycol solution through, and we actually have the ability to plumb work holding into that. Not saying that you would have to have a build plate or a subplate with cooling running through it. We could basically just use a vise or vise jaws to run cooling through. But right now, how we handle it in terms of work holding, we'll tap into our cooled build plate, which is really just a subplate. It's not the actual surface that we're depositing on. It's usually the surface that we're bolting the substrate to that we're depositing on. But vise jaws, you can make cooled vise jaws that would work with our system. You could have, custom fixturing as well.
This next question to SolidCAM, are there any solutions in development for dynamic additive parameter changes like laser powder, wire speed, to vary those parameters for different heights of the part?
Yeah, so on the software side for the CAM, the quick answer is yes. We will be able to have control of pretty much any key parameters that you would like to change. A lot of that is going to be limited more so on the hardware interface, whatever controller that particular solution is using, and then obviously the practical limitations of what factors you can actually vary in a given platform. Because again, it's not going to be available just for the Meltio system, but any type of DED head that we might develop compatibility for, they may have different sets of parameters that may not be universally applicable back and forth between systems.
This next audience member raises the issue of standards specifically related to the oil and gas industry and the aerospace industry, and the appropriateness of hybrid manufacturing for standards. He lists some, but the question he gets to is, have you done any collaboration with institutions or governmental programs where hybrid has been developed or is under development specifically with regard to specific sector industry standards?
In short, yes. The U.S. Navy has a tech pub for wire-fed directed energy deposition. So that is certainly a spec that we have started to adhere to for working on components that would fall into those categories. Each industry certainly has their own specifications, but at the end of the day, this technology is laser welding. So we're using a commercially available welding wire. The power source is different. So we would fall under kind of the AWS, American Welding Society spec for laser welding.
This question overlaps a little with an answer you gave, but it's a kind of important fundamental issue. So let's go there again. He asks, what are the envelope limits of size for the additive manufacturing portion of the hybrid? Is it fixed or does it depend on the machine it's installed into?
Yeah, so I actually missed this portion, so I'm glad we brought it up again. When we integrate into the machine tool, you don't lose travel. So some of the machines that we don't support, the reason we don't support them is you would have to essentially limit how much travel you would have in terms of x-axis or y-axis to avoid a collision point. The machines that we support, you do not physically lose any travel. Now, when it comes to 3-axis, it's very straightforward. You're simply shifted between the milling spindle and the additive head. So if there's a 12-inch shift, if you were to print a part max travel of the 3-axis machine, you certainly could. You just couldn't machine the max travel of that machine because you'd have to have a manual operation to move whatever that shift distance was. So you're not losing travel. It is shifted. For 3-axis machines, pretty straightforward. For 5-axis machines, it depends on the configuration of the rotary table. So we focus all on table 5-axis machines. We don't currently support any head 5-axis or head table 5-axis machines. So when we talk about our UMC or Haas VF line with 5-axis rotary tables, once again, we don't limit how much travel you have. In the example of a UMC, let's say 750, you do have about 11-inch shift in the x-axis. Y is somewhat negligible, about an inch or so in center line distance. You don't lose travel. However, you can't deposit fully at, x minus 30 inches, that's total travel of the x-axis. At B positive 90, you would have to use an alternate rotary solution. So you have that overlap, and that's where it becomes somewhat of a robot. If anyone's ever seen kind of a robot collision point or hindrance point, it's very similar to that. You're going to be able to, or you would need to use an alternative rotary position to handle kind of that overlap point. When it comes to just the head is retracted, so the head retracts within probably about 5 or 6 seconds. The doors fold up on itself with the head mounted where it is from spindle face to the bottom or the collision point. to keep things, straightforward. You have about 4 to 5 inches depending on Haas machine. So at B90, worst case scenario, you might have to use a 1 to 2 inch longer gauge line tool to give you, 8, 9 inches of clearance if you were working close to center point of rotation with the tilt axis at 90 degrees with a BC configuration machine. So, worst case, if you're just doing machining, you might have to use a 1 to 2 inch longer tool depending on where you're working on the machine.
Does coolant left on the part after machining affect welding?
So the laser process will vaporize the water. What you don't want to have is gas porosity from the water being vaporized, getting trapped into the weld. You also don't want the solids from coolant left over in the weld. So to avoid this, you can have an automated air blast. Depending on the requirement or application, you may want to have a manual operation to clean the part with, isopropyl alcohol, ensure that there's no coolant left on the component. Ideally, if you have, a very high requirement for cleanliness, the system will certainly process it. One of our kind of fun demos that we'll run at trade shows is we'll have a layer of coolant left on the part and then weld over top of it, and makes for a nice little show. But if you had a high requirement where you wouldn't want to do that, I would try to focus on building the part fully before you went to machining. But if that's not the case, worst case scenario, having a manual machining operation or manual cleaning operation, or some type of dry machining operation to avoid having coolant on the area that you want to deposit.
We have a few minutes left and a couple more questions. One of these doesn't directly relate to hybrid, but it asks to SolidCAM. What types of additive technologies, broadly in general, what types of additive technologies is SolidCAM developing software to support?
Yeah, so there's a wide range that we will eventually be able to cover. For right now, we're going to be focusing primarily on DED hybrid platforms and potentially FDM hybrid platforms as well. Those are we showed the demonstration for the DED, and FDM is very similar, just with slightly more advanced toolpaths, more support structures, different infill patterns. Those will be the first 2 that we target, and those will be technology, not system dependent, right? So like we mentioned, any other DED platform could technically use the same general toolpaths and CAM package as the Phillips platform would be able to.
This question similarly is broader than hybrid. It asks, based on your experience, what 3D printing technologies do you see fitting in well with a traditional machine shop?
Probably right off the bat, the simplest FDM is probably the most accessible and a great way to get in the door if you're a very traditional shop that really hasn't started to adopt additive yet. It's a very low cost, very easy way to kind of just start figuring out what that technology can do for you. Very useful for everything from organizational tools to even some basic fixturing and tooling. From there, platforms like these hybrid solutions we're talking about are really appealing in a lot of cases. Like I mentioned, you kind of get 2 for 1 as far as the machine tool. It's a system that a lot of people are already familiar with. Everyone's run a Haas machine. They all know how they work. They all know what their capabilities are. So the fact that you can get that just with this extra add-on where, well, now we can kind of dip our toes into additive a little bit and to a pretty serious degree with the capabilities there. So FDM is a great starting point. And then obviously these more capable kind of DED combination machines are a really good next step.
And here is what might be the final question we'll get to. Brian, the cooled subplate. Talk about that. The audience member asks specifically, is that part of the Meltio integration?
That's part of the Phillips hybrid integration. So it's something that our team at Phillips Corporation, we design and use the Rotary Unions, especially when it comes to 5-axis machines. That way, when we talk about a table 5-axis machine, we have to have a Rotary Union. So that's something that we develop, as well as make custom for our customers. So that way, if you're using a particular type of work holding, we incorporate that into our design. That way, if you're using Lang or 5th axis, we'll use the bolt patterns for those subplates or fixtures.
All right. I think we'll end it there. That concludes today's webinar. I want to thank our presenters, Brian Christoponis of Phillips Corporation and Pete Genovese of SolidCAM. Guys, thank you.
Thank you, Pete.
Thank you.
Learn more at solidcam.com and at phillipscorp.com. An email with a link to a recording of this webinar should come to you soon. So to our audience members, thank you for your time today. I'm Pete Zielinski with Additive Manufacturing Media.